Hi, everyone. Good evening. Welcome to this session. Um, Josh Wiedemeier will be speaking about there and back again, reverse engineering, and Python binaries. Welcome and welcome to the session.
Alrighty, hopefully everything is working. Hello everyone, how was your first day at PyCon, or first day of the talks at PyCon? I guess I should clarify. I'm Josh Wiedemeier, I'm a PhD student at the University of Texas at Dallas, and for the past couple years I have been studying decompiling Python binaries, so going from PYC files back to .py files. But before we really dive into it, I want to start off with some background, make sure we're all on the same page on some common misconceptions of what happens when you actually run Python code. Oftentimes people are just running scripts and they send it to Python and they get a result. We're happy, but the Python interpreter doesn't actually read your source code directly. First, it goes through an intermediate step with the CPython compiler, which will compile it to bytecode, which is then set to the interpreter. I clarify CPython because I've talked to a few other people in the field, and when I just say Python, sometimes people get mad at me for not including Jython, PyPy, or any other kind of implementations of Python. So I want to be very concrete that I'm looking at just CPython here today. And if you want to see this compilation step done separately, if you want to get those files out to just read it, you can use the Python compile all module, which will put those PYC files in the Dunder PyCache folder. So from this simple example, at least I hope that's still working. Maybe if I go back and forth. Let me try unplugging and replugging. It's working up here, not up there. All right, well, what you don't see is that I'm going to introduce a simple example that we're going to continue working with through the rest of the presentation. Also, feel free to interrupt me at any point if you have questions. I know it's a little non-standard, but my goal is to go kind of low and slow through a straightforward example. We're going to walk through what actually happens at low level for most people, but if the CPython team are in the audience, please forgive me for criminally oversimplifying the Python interpreter. But yeah, we'll walk through what happens at each bytecode instruction just to get a good intuition for what's happening at a relatively low level when you run your Python scripts. Then we're going to throw away the source code and start to work backwards. So from the bytecode, how can we get the source code back? Well, hopefully the slides will come back online. Otherwise, it'll be really difficult to show you what's going on. You'll just have to trust me. Oh, it was there for a second. Flickered, yeah. It flickered again. Well, I guess while I'm still stalling for time, show of hands, how many of you guys would consider yourself to be like, have a surface level familiarity with Python bytecode? Like, how many people have heard of Python bytecode before? All right, good show of hands. How many people would consider yourself kind of deeply familiar with it? Like, if I showed you any instruction, you could probably figure out what it does. A much smaller show of hands. Okay, so we're only going to go through a subset of those instructions today. You don't have to worry about too much. Well, this is unfortunate. Sure, yeah. We can take a break and try and sort these out. Sure. I mean, I don't think there's been a much stuff to ask questions about, but yeah, we can take a short break while we figure out the technical difficulties. I guess if you have any preliminary questions before the talk starts, then then you can come up and ask them.
Can you recite every bytecode?
Recite, no. Recognize, probably. Especially, it depends on which version you're talking about. Because something that I'll bring up later is that the Python bytecode specification keeps changing every year, mostly thanks to the wonderful CPython team. So every year, people that are making Python decompilers have to update themselves to try to support the most recent versions of Python. And that's been really one of the biggest challenges in automating Python decompilation.
Is it getting bigger and bigger, or are they removing stuff too, or just adding more?
They're limited in the total number of opcodes they can have because they want each opcode to be 1 byte. So there's a limit on how much they can have. I know in the recent versions, they overflowed that a little bit and added some call intrinsic opcodes that let them have a little bit of a garbage bin for miscellaneous functionality. So, but generally, some have been removed, some have been added. Most of the time, a little bit under 10% of the opcodes are either add, deleted, or modified. But Python 3.11 in particular, I think almost a quarter of them were affected, which was a pretty big shift when they swapped over from using a block stack to track exception handling structures and moved over to using an exception table, which ultimately was a very good change. Helps Python run faster, and also it is more understandable. But it did mean that the decompilers had to start reading a new metadata table.
Maybe you were going to get into this during your presentation, but since we have a little time, maybe.
Different port? Yes. Okay, let me try the one on this side. Sorry, one second.
First things first.
Okay, can you repeat the question, please?
No, go ahead with it. Oh, you still don't have it.
I mean,
I was going to ask while the screen comes on, if you can give a little bit of a background on how you became interested in this problem.
so really what happened is when I finished my undergrad, the job market wasn't looking so hot. It was some like 2021, 2022, and I had a professor who really liked me and said, come join my lab 3 days before the application deadline for the PhD program. So we started knocking on doors, trying to find anybody who would give us some recommendation letters on a 1-day notice. We found some people. His lab, and ultimately we're here today, but his lab was working on trying to fix issues in existing Python decompilers. But ultimately we found that the maintenance effort required to keep up with the Python update cycle was a little bit much, and that was a big challenge that was preventing the scalability of things like uncompile 6. So we had the bright idea of trying to make our own Python decompiler that uses machine learning to automatically learn parts of the bytecode specification, and that allows us to kind of rapidly scale up to handle the most recent versions. So that's, originally it was a project that I was put on, and then I really fell in love with it and started pushing forward in new frontiers here.
I mean, it's kind of a similar.
All right, almost. You guys can see my speaker notes.
I feel like this can be deferred.
All right, well, that's closer. Like, get out and get it back in? We're back online. Thank you for your patience. OK, so I guess I'll try to jump right into it, and I'll see if I can catch up and get us back on schedule. So yes, when you run your Python, so let's quickly get familiar with this basic example where we just have a function that is going to try to open a file, and if it is able to open the file, it will print all those lines to the screen. Straightforward example, and we're going to walk through running just the top level script. We won't even we won't go step by step through everything, but ultimately, after you compile this script, you'll end up with two code objects. You have the main code object, which represents the top level script, and then every function and class will be compiled into its own code object and form a code object hierarchy. This abstraction is helpful for us because what we'll soon see is that when we're running it, and ultimately when we're decompiling it, we are able to consider each of these code objects independently. So the anatomy of the code object, that's important. We have instructions. That's generally what we are most concerned with. And then there are some kind of data tables. Either they're semantically important, having the variable names, the constants, some other useful information. And then there's some other tables that I'm not showing here. And then there's also some debugging metadata table, like the line number table. So each instruction or most instructions will be indexing into one of these tables. So like these constant instructions are going to be indexing into the co-consts table. The store fast, load fast, this kind of family of instructions that operates on local variables is indexing into the co-var names table. Just a side note, for this talk, we're working in Python 3.9 because that's what I learned in. It's, I think, one of the easier versions to understand the bytecode. And in more recent versions, you'll end up with more opcodes, so this fits on the slide better. So if we're going to go step by step through just the top level script in the main code object, the first thing that we're going to do is start to create the dump function. We're going to load the dump code object. We don't actually care what's in it. It's going to go on a value stack. The Python interpreter at a high level implements a stack machine. So we can push and pop values onto this value stack. So if you've ever worked with any kind of stack-based calculator, like does anyone own a reverse Polish calculator in the year 2024? Okay, we have one. Let's go. Okay. So we'll make that function object. We're going to store it in the local dump variable, and now we're done with defining the dump function. Then to check if name is main, just make sure we're running the script and not importing it. We're going to load the global dunder name variable, load the main string from the constants table, check if they're equal. It will pop those two items off the stack, push true, because they are in fact equal, thankfully. And then to implement the if logic, we're using a conditional jump, which if that value were false, we would have jumped straight to the end, but it wasn't, so we're not going to jump, and we're just going to keep going. We're going to load that dump function from the locals table, load up the test.text string, and then we're going to call the dump function. Here, we don't actually care about the implementation details of dump. Just imagine that I walked through that step by step, and we returned back. It doesn't return anything, so we get none back on the stack. We'll get rid of it, because we're not actually using it. And finally, we return none, because every function in Python has to return something. And if you do not return something, none will be returned for you. So that's how we run Python. And when you're distributing a Python application, unless you are working in open source, where you can just send people your .py files, if you want to send out some executable file, or you want to hide your source code in some way, I guess a notable example here is the Dropbox client was distributed Python. You will compile it ahead of time and then package it with the interpreter with something like PyInstaller. A lot of places will have like their in-house packagers, and that will get you an executable binary. And when we're going back, first we'll unpackage the executable binary to get those PYC files back, and then we'll decompile that PYC file back to Python source code. And this decompilation step is really the focus of the talk today. So to decompile by hand, you really have three main steps. The first one is segmentation, where we're going to identify statement boundaries, break down the bytecode into something that's a little bit more manageable for people to deal with. The second step is statement translation, where we're going to translate each statement of bytecode into a statement of source code. And then finally is control flow reconstruction, where we're actually going to stitch those kind of floating statements back together to get something that resembles the original script. So for the decompilation part of this, we're going to be looking at the dump function, which is chosen because it's compact and it shows a lot of language features and not a lot of space. If we just look at it straight on, the first thing that I want to do is not look at it because it is big and hard to really digest on its own. So the first thing we're actually going to do is try to break this up into manageable statements. The easiest way to do this is to refer to the line number table, which is a debugging symbol that will tell you what is the start of each, or which opcode starts each line. And actually the built-in dis module will do this for you. Dis is a great module. I recommend looking at it. I recommend using it if you're interested in understanding how your functions are implemented at a lower level. But for automatic decompilers, this isn't quite enough because the LNO tab can be unreliable. So just as a word of warning, don't take the LNO tab as your sole source of truth, because you can do things in source code like putting multiple statements on one line or spreading one statement across multiple lines that will cause the line number table to not truly represent the source code statement to bytecode statement mapping. In the worst case, the line number table can be entirely removed after compilation just because it's a debugging symbol, so your script will still run correctly even if it's gone. But for our example, the line number table is acceptable, so we're just going to move forward with that. So for statement translation, we're going to symbolically imagine what the Python interpreter might be doing when it's running this code. And that will let us implement that logic in Python source code. And we're going to make sure that we just ignore any external control flow because we'll come back to that later. This is the fun step that feels like decompiling. It makes you feel really smart when you're doing it. So for this particular line, we're going to load the print symbol from the globals table. We're going to load the line symbol from the locals table. We're going to call the print function with line as the only argument, so that return value of print line will be on the value stack, and we pop it to get rid of it. So the logic here is we're just calling the print function. And by following the bytecode step by step, you can start to see what the Python implementation of that logic will be. And by digesting one statement at a time, it makes it easier on our puny human brains to wrap around the program logic. This jump absolute is actually going to offset 42. We're already at offset 58, so it's going to be jumping backwards. There's no single statement in Python that's free of context will implement this jump, so this is external control flow. We're going to come back to it in the next step, but we can ignore it for now. So what we just did for that print line, we're going to do that for every statement. In the interest of time, I won't be going step by step through every single statement in the dump function. But ultimately, you can see a try. You can see the file being assigned to open. We get the same lines out as were in the original function, but they're flat. We don't know what the indentation is. Technically, we don't know what the order is, although in 3.9, the offset order matches the source code order for the most part, although that's less true in more recent versions. So the next step we're going to look at is control flow reconstruction. So for this, we're going to zero in our attention on these control flow instructions that either influence the block stack or they influence the which instruction is going to be executed next. So the setup finally is going to push an exception block onto the block stack, which is used for tracking exception handlers, as I mentioned a little bit earlier when we were going through the technical difficulties. Obviously, jumps are going to jump around in the bytecode. You have unconditional jumps, you have conditional jumps. We have returns, which will return values. We have re-raises to raise exceptions. We have for iters for iterating through in for loops, which has native bytecode support, which is always fun. But notice that the call function is omitted from this list because the only things that a function call can do in Python is that it can either return back to you, or it can raise an exception, or it can also kill the program. If it kills the program, it's no longer our problem. If it raises an exception, any instruction can do that. It's not special. And if it just returns back to us, we can continue on our merry way. So as far as the control flow of one code object is concerned, if we're just trying to reconstruct the source level control flow, we don't actually need to look at the function calls, which is very nice. So the first thing we're going to do with these control flow instructions is build a control flow graph. So for each control flow instruction, we're going to keep track of any relevant information. So in the block stack, we're going to see the exception block get pushed on. And the next thing that will be executed is the next thing in offset order, which is some stuff, and then the pop block. When we get there, it will pop off that exception block, so it's no longer relevant. If an exception were to be raised in that area, it would go to the exception handler that was marked in the exception block. And then if there's no exception raised, we'll go to this jump forward to jump past the except block in the bytecode. And then we get to this for iter, which either you can continue into the body of the loop, or if the iterator is completed, it will send you off to the end of the loop. If we return, then there's no more control flow. We're done here. A pop jump if false is a conditional jump, so either it will continue through to the next thing, or it will, in this case, jump back to the loop header because it happens to be the last statement in the loop. And then an absolute jump is unconditional. It will always jump. We've already dealt with the for iter, so let's go over to the exception handler. This jump if not exec match instruction is only used in the conditional exception, so like except file not found error, except IO error, except stop iteration error, all these kinds of things. And that will say if the exception type matches the given type, we'll go into the body, which in this case just returns a value. And then otherwise, there's no other options here. It's just going to re-raise. So now we have a completed control flow graph. And we also have a flat list of source code statements. On their own, these things, maybe you can start to see how we're going to put it together, but we do need to put them together. So we're going to associate each statement with the first instruction in its bytecode and tack that into the control flow graph. And already you can see that this is starting to get much more readable. This is starting to get much closer to the Python that you know and love. To actually fully complete the process, like in this simple example, some of you may be able to already start seeing the patterns of how all these control flow blocks fit together. But to stay principled and to make sure that what we're doing will work even when we're looking at larger, more complicated examples, we're going to walk through a classical method of control flow reconstruction, where we're going to look for primitive control flow structures, individual control flow blocks, and then condense those nodes iteratively. So we're going to start with a complex control flow graph and end up, hopefully, with a single node, which is the simplest control flow graph. And we're going to work from the bottom up. And then when we get just one node, we're done. So working from the bottom, the first thing that we see is this if statement, which has, in this control flow graph, has no other stuff interacting with it, which is what lets us identify the primitive, where either it's going to go into the body or it's going to jump around the body. And both the if header and the if body will eventually go to the same place. This lets us condense the if header and the if body into one control flow node, and we can substitute that back into our control flow graph. And now we have a slightly simpler control flow graph, and we continue the process. The next thing we see is this loop structure, where either you are going to go into the loop and jump back to the header, or you're going to exit the loop and go to the outside. In this example, we're not considering breaks and continues and such, but those do pop up in the wild. You'll have to deal with them eventually. But this lets us condense this loop down. So now we have a much simpler control flow graph. The next thing we see is just a natural sequence. You may also call it a basic block, but I've had people get mad at me for calling it a basic block because technically it contains some other control flow that's going on here. So I will call it a natural sequence just to make sure I'm not stepping on anybody's toes, where that's just one thing happening right after the other. And the way we condense that down is just put that thing right after the other in the source code. Then we see the conditional except that we were talking about earlier, where either it's a file not found error and you will go into the body, or you're going to re-raise. The re-raise is done implicitly, so this all gets condensed down into one node, which is the except file not found error, and then the body indented one line. And then the try except primitive is the largest primitive that we'll see today, where you have the try header, the try body. If exceptions are raised in the try body, you go to the exception handler, and then at the end of the try body, you jump past the exception handler and go to whatever comes next. This puts us, once we simplify that down by putting together the try header, try body, and the exception handler, we are left with just two nodes left in our control flow graph, and one more natural sequence, and we have condensed all the way back down to one node. And if your memories are very good, you may recognize this code as being pretty much exactly what the original dump function was. But we aren't quite done yet. First, even though we already have the code for the dump code object, we want to place it in context. We want to finish the whole PYC file and not just do one code object. So we will decompile each code object independently. So now we have the code for each of the code objects. So we have main, we have dump. So imagine we just did that same process, but also for main, but it went much faster because main is much simpler. And then anytime you see a function definition, a class definition, something that invokes that code object hierarchy, we can just insert the code object here. And then you end up stitching together all of the code for the source file. So at this point, we're done. We have decompiled by hand the entire PYC file, and we've gotten back to the source code. The hard part here, though, is that Python is constantly changing, as I was talking about earlier. Every year, opcodes are removed, modified, deleted, added. And so if you want to keep your skills sharp, you always have to be looking out for what's coming down the pipeline. In the CPython development, you need to be using the dist module to look at Python bytecode. How is the compiler generating these code patterns if you want to translate them accurately? If there are any quirks, a lot of it's a game of edge cases. You just have to buckle down, take a look, and start digging in. But what if we don't want to do that? What if we just want someone else to automate it for us? That would be better. There are a couple of popular and available automatic Python decompilers. The first one that I want to talk about is Uncompile 6, which is currently the most popular Python decompiler. And this uses version-specific parse grammars to slot into a generic decompiler interface, and that's how they get their maintainability. It supports all the Python versions 3.8 and below, so everything up to but not including 3.9. If you want to decompile some really old Python, like I know there's still some 2.7 floating around, whoever's using 2.7, please update to Python 3. But maintaining these grammars is labor intensive. So when you get into 3.9, 3.10, and especially 3.11, the coverage and accuracy of Uncompile 6 has suffered. So what my research lab has been working on, I think I was also talking about this a little bit during the impromptu Q&A, is Pylingual, which is a neural decompiler that uses custom transformer models to learn parts of the bytecode specification to perform the segmentation, translation tasks that we just did. And the control flow reconstruction is done mechanically. And this is actually available online at pylingual.io, if I'm allowed to shill a little bit. And importantly, because we've all hopefully learned not to trust the output of language models without verifying it for ourselves. We verify the correctness of the decompilation results by recompiling that resulting source code and comparing it to the original bytecode that you put in. It looks like we still have a few minutes, so I've got a couple of demos lined up that we can go see. The first one is a successful demo, which is, let me see if I can drag this over. The example that we walked through today, just to show that yes, you can automatically decompile it. You'll see that the else is a little bit interesting, but if we were to raise an exception, we would have returned anyway. And ultimately, the bytecode that you get is the exact same. So if you have a nice case, it will just work. The second case I wanted to bring up is actually a failure case. So what happens when the decompilation output is not correct? We can detect that. We can say, okay, these code objects were decompiled successfully, but something at the top level went wrong. And if we look at the difference in the bytecode, most of this is actually correct. But right down here, we're correct right up until this 1310, and then there is a statement, this load const store name, that has been omitted from the decompilation result. So what we can do is use the skills that we learned today to actually fix this issue. We can fix this error. So let's look back and see. We were using extended arg, putting that in the list, and right after that, we're doing that. This is actually a file from xdis, which is a cross-version disassembler, kind of an extension of the dis module that is maintained by Rocky Berenstein, who's an inspiration to us. Let's see. So if that was extended arg equals 44. And let's see if that makes it any better. It probably will make it a little bit better, but not much. There's still another issue. Let me get the patch bytecode diff. And right at the end, there's some additional stuff that also was omitted. So what we have def op, name op, jrel op, jabs op. So we can actually add this over at the very end. And here, all I'm doing is using the same skills that we learned today to look at this bytecode statement and decompile it by hand. So I'm seeing delete name, def op. So def op, delete name, name op, jrel op, and jabs op. And let's try that. So we're implementing this bytecode logic in source code. And now we can see that we got everything there. So you can, by knowing how to decompile Python by hand, you can take almost correct decompilation from an automatic tool and turn it into fully correct decompilation and kind of close the loop that way. So that brings me to the end of my talk. And today we covered how to read Python bytecode, how to decompile Python bytecode by hand, and how to use automatic tools like uncompile6 and pylingual to decompile Python bytecode and save you a little bit of headache. So yeah, that's all I have for today. Floor is open for questions.
Hi there. Are you able to detect the version of bytecode, or do you have to have knowledge of what version it is already?
There is a magic number at the start of the PYC file that tells you what version was used to compile it. I will definitely add the caveat that the verification check assumes that the PYC file was compiled with kind of a stock standard CPython compiler. So if somebody is doing any extra obfuscation or they're using some other compiler like PyPy, then that accuracy check won't be reliable. But as long as it's compiled with CPython, then the accuracy check is reliable. And fortunately for us, CPython is pretty dominant in the Python compiler landscape.
Thank you. You actually answered my follow-up.
Oh, perfect.
Yeah, so I've seen that like in 3.12, they've been putting extra compiler optimizations in. Has that made bilinguals work any harder, or does it just cope with that automatically?
We had to do a few updates to the control flow reconstructor, but surprisingly, the transformer models were able to seamlessly handle the changes. The accuracy decreased by a couple of percentage points, but ultimately it was not too much of an effort, especially compared to the work that we had to do to support the exception tables in 3.11. I heard the JIT stuff coming in 3.13. I was very glad to hear that that is happening at runtime. So hopefully that won't be too much of an issue for us, but we'll find out when we get there.
We'll be taking last question.
Yeah, so you mentioned the word you used was bytecode specification, and I'm wondering, it's not quite a formal specification, right? So it's very interesting to use transformer models to do this. Open-ended question, can you comment on how you're depending on the wording of I assume this is the DIS documentation?
Yes, this is the DIS documentation.
So yeah, if you can comment kind of on that not being a binding specification, I guess.
So the way we actually train let's see, the reference that we're making directly to the DIS documentation is checking what bytecodes exist. And that's needed for the disassembler. Learning the actual semantics of the bytecode is done entirely in a data-driven way. I was actually at the start how they were talking about PyPy servicing some billions of downloads. At least about 1.5 million of those were me. I've been downloading a lot of PyPy. Thank you for your fast API usage. I can get a lot of source code samples that can be compiled into whatever version I want, and then use that to train these transformer models to learn how the bytecode actually behaves. So I'm training them specifically for the segmentation and translation tasks, rather than trying to generically understand every part of bytecode. All right. I think that was the last question. Or there?
Yes, that was the last question. Thank you very much.
Thank you so much. And I'll run in the hallway afterwards if there's anything that you don't want to ask on the big stage.